Hey guys, I just wanted to take a second and clarify what we were talking about earlier today, specifically the percent dissociation of a concentrated acid versus a dilute acid. So notice I didn't say strong versus weak, but concentrated as in, for example, 1 molar versus more dilute, a 0.1 molar. We're going to consider the same acid. Now I just made up an acid, a weak acid, which we're just going to call HA. And I'm going to tell you that its Ka value is just, again, made up value 2 times 10 to the negative fifth power. So in water, we know that our weak acid, HA, is going to dissociate. It's going to dissociate into that conjugate base and the hydronium ion. So basically, that means that our Ka value comes from the fact that we have the conjugate base formed with the hydronium ion all over the concentration of our original acid. So the idea being is that we're going to go ahead and figure out what would be the dissociation for this more concentrated versus this less concentrated or more dilute acid. So we know we could make a rice box. So our initial concentration here was 1. And then we had no concentration here. And since it hasn't dissociated yet, 0 and 0 here. We know that we're going to lose some of our weak acid so that we can make some of our conjugate base and the hydronium ion. So our equilibrium concentrations are 1 minus X, X, and X respectively. So our Ka expression is basically going to be X squared over 1.0 minus X. And that's all going to get set equal to our 2 times 10 to the negative fifth power. Now, we could go ahead and solve for X, and in fact, when we do, we get that X is about 4.0 times 10 to the negative third power. So that means our hydronium concentration is about 4 times 10 to the negative third power. So if we wanted to find our percent dissociation, the percent dissociation is basically going to be how much hydronium ion I have in solution compared to the concentration of my initial solution. So that's going to be our 4 times 10 to the negative 3 divided by our initial concentration of 1. So our percent dissociation is about 0.4%, which is reasonable. Let's consider the same thing, only now let's focus on a solution that was more dilute. So what's really going to change in this situation? Well, the only thing that's really going to change is that my concentration that I started with is less. So this would be 0.1, 0.1, and then this would also become 0.1 as well. So really when I'm solving, all I'm doing is changing that value. And so we could put this into our trusty dusty calculators, just as we did, and solve for X. When I do, this time, I get that X is equal to 1.4 times 10 to the negative third power. So it's about, roughly 3 divided by 3 times less, which shouldn't be surprising because actually it's going to be the square root of 10 times less. If you think about it, we're basically taking this value and we're multiplying it by, or dividing it by 10. So when we take the square root here, we're basically taking the square root of X squared divided by 10. So that having been said, it makes sense that my value is going to be less here. So this number is smaller. However, remember, we're comparing that 1.4 times 10 to the negative third compared to its original concentration, which before was 1. But now my concentration is 0.1. So now when we divide, we actually end up getting 1.4%. Notice my percent dissociation here in the concentrated is actually less than my percent dissociation here in the dilute. So the more dilute my solution is, that means that the more it dissociates in terms of its percent. That doesn't necessarily mean that you have more hydronium ions. It just means that the part of dissociation is larger. So we can summarize what we just saw here with the following visual. So, as acid concentration is increasing, I hope it makes sense that more acid or higher acid concentration is also going to mean more hydrogen ions in solution. However, since this is probably going down by a factor, if we say this is 1 and we say this is 0.1 and maybe this is 0.1, yes, we are making more hydrogens, but more hydrogens compared to much smaller numbers here. Remember that hydrogen concentration that we're talking about, H+, compared to the original concentration, well, this is going to go down some, but this goes down a lot. So that's why, as our concentration is decreasing, our percent dissociation is actually increasing.